Having created a background on potential energy in the previous video, we will try to get an expression for potential energy in this video. So what did we discuss? We said that if we have a spring and you apply force on to the spring, it gets elongated by distance x centimeter or meter or whatever, right? When you apply a force on the spring and it gets elongated, that means we've done work on the spring, right? Because work is force into displacement. So since we have applied a force and there is a displacement, we can say we have done work on the spring. And this work done, which is done on this spring, is stored in this spring in the form of elastic potential energy. So what is the potential energy stored in the spring? So if I write down over here, potential energy stored in the spring is equal to work done on the spring. Right. Now the most common formula or the general formula for work done is force into displacement. Here I am tempted to write for force F because that's the force applied on the spring and displacement is x. So I am tempted to write over here is equal to F into x. And I may start thinking that F into x is the potential energy stored in the spring. But this is not right. This is wrong, right? So let me get this off. Right? This is wrong. Why is it wrong? It is wrong because for this elongation to happen from 0 to x centimeter, the force which was applied is not F. It is not constant. It keeps on increasing as we move from 0 to x. So I cannot take F as a constant force for this elongation x. And so I'll have to use integration between the limits of 0 and x to find out the work done. Right? For doing that, what I'll do is I'll take up a very small displacement, let us say a very small displacement dx, right, between 0 and x. I'm focusing my attention on an extremely infinitesimally small displacement dx. And let us say for this displacement to, or elongation, I should use the word elongation to happen, the force applied is F. Since this elongation is extremely small, this force can be taken as constant, and therefore the small amount of work done for this elongation dx will be given by dw is equal to F dx. Right? dw is equal to F dx. So this is the amount of work done for the small displacement dx. And if I want to find out the total work done for 0 to x, I'll integrate this between the limits 0 to x. Therefore total work done is equal to integration of dw from 0 to x. Right. So, and I'll come back over here. Right. So I'll write down over here the potential energy stored in the spring is equal to work done on the spring is given by integration of 0 to x dw, and this will be equal to 0x dw is equal to F dx. Right. dw is equal to F dx is equal to integration of between the limits 0 to x. For F, I can write down F into x. F is equal to kx. So I'll write down over here for F I'll write down kx dx. Right. And if I do integration of this, potential energy stored in the spring, if I denote this by, let us say, u, therefore I can write down over here, or let me use this space, therefore u is equal to integration of 0 to x kx dx. Right, kx dx. And if I integrate this, I'll get k of x square by 2 between the limit 0 to x, and therefore u will be equal to k x square by 2 minus 0 by 2, and this will be equal to half k x square. U is equal to, and this is how I get an expression for the potential energy stored in a spring. U is equal to half kx square. Right? U is equal to half kx square. What does this mean? This means that if I have a spring, right, which has got a spring constant of k Newton per meter, I'm taking SI units, and it is elongated by distance x in meters, then the potential energy stored in that spring would be half kx square, and this you would get in joule. Right? So this is the expression that I have obtained for potential energy stored in a spring which is elongated by distance x. Also, please keep in mind that this is also equally applicable if you are compressing the spring. right? If I compress a spring by x meter and it has got a spring constant of k Newton per meter, the energy stored in the spring would be half kx square. So this formula is applicable not only for elongation but also for compression. Okay, what we'll do is that in this next video, right, in a very short video which I'll do after this, we will look at how the potential energy or the energies vary, and we'll look at conservation of energy of this particular spring, right? Thank you.